The self-propelled transporter, a wheeled transport wonder, an all-terrain expert on challenging surfaces, steep inclines, and descents. They are used wherever other transport systems are not up to the job. Self-propelled transporters can carry up to 7 times their own weight. If several modules are used together, they make light work of even veritable giants. These transporters boast massive engines producing more than 500 horsepower. And an unusual chassis with 8 wheels per axle line. Their biggest advantage? Maneuverability. They can move sideways, diagonally, or even turn on the spot. The headquarters of Goldhofer in Memmingen, Bavaria. Over an area of more than 100,000 square meters, these experts in specialty vehicles, with around 800 employees, manufacture a wide variety of transport systems. Trailers, semi-trailers, low loaders, aircraft tugs, and transport modules. Both towed and with their own propulsion systems. The latter are also known as self-propelled transporters. These consist of 2 main components: the drive module, also known as the power pack, and the chassis. The 6-axle chassis of the self-propelled transporter has 48 wheels and can transport heavy loads weighing up to 235 tons, even though it weighs just over 26 tons itself. The attached power pack adds another 8.6 tons. This contains an enormous 6-cylinder V6 turbo diesel engine. With a displacement of 12 liters, it produces around 530 horsepower and develops around 2,100 Newton-meters of torque. The frame for a drive module, 5 meters long by 3 meters wide, and 86 centimeters in height. It's delivered in the transport position, upside down. Before they can install the individual components of the drive system, the technicians first have to flip this 2.6-ton powder-coated special steel giant. At the heart of the power pack is the motor. This 6-cylinder diesel engine from Deutz weighs just over 1 metric ton. A few things have to be done before it can be integrated into the power pack. Therefore, the technicians first place the motor on an assembly stand.
Among other things, it comes from Deutz with a protective coating to prevent corrosion. First, we have to remove that, then we add our components one by one, a gearbox, pumps, and so on.
Mechanic Stefan Kolmus uses brake cleaner to remove the corrosion protector from the parts of the motor where the components are to be installed. It's very important that even the screw threads are completely free from grease, oil, and dirt. This is because, due to the tremendous vibration of the motor, the mounting bolts are also glued in place with a special adhesive. The first part to be mounted is the clutch, or to be more exact, the dog ring of the clutch. A special adhesive is applied to the mounting bolts. Stefan tightens the bolts, first with an impact driver, and then using a torque wrench. Meanwhile, at the power pack frame, the technicians start with the tubing for the hydraulics. This self-propelled transporter isn't operated mechanically via a drive shaft, but hydraulically, that is, using oil pressure. That's why this self-propelled transporter is also known as a powered hydrostatic-driven tractor module. The hydraulic drive enables smooth movement without gear shifts, in both forwards and backwards directions. The power pack's hydraulic tubing is subjected to up to 420 bar. The tubes range in diameter between 8 and 42 millimeters, and they have a wall thickness of between 1.5 to 3 millimeters. The hydraulic control panel is already pre-mounted. It can be operated manually or by remote control. The control unit has to be in exactly the right position so that the next components fit next to it. Now the mechanics attach the hydraulic tubing to the valves and pressure connections. The line with the marker pen indicates the joint has been tightened. Back to the motor. The hydrostatic drive means that this system does not use a regular gearbox, but a pump splitter gearbox. Mechanic Stefan Kolmus sprays the bolts with a metal protector. He then lubricates the drive shaft and mounts the clutch damper on the transfer case. He tightens the bolts to hold the clutch damper and then checks it for ease of motion. He can now attach the transfer case to the motor.
The motor produces rotation. The pump transfer case transfers this rotation to 3 separate outlets. The pumps are mounted to flanges at these outlets. At the bottom, we'll mount 2 pumps for the propulsion system and then 1 duty pump at the top. So the rotation is then used to generate pressure.
Propulsion pumps are only used for driving the axles. The duty pump produces the pressure to raise and lower the chassis and to turn in different directions. In practical operation, the self-propelled transporter is operated by means of radio remote control. The driver can use this to accelerate, brake, and turn, as well as to raise and lower the chassis. The radio remote control can also be used to drive several self-propelled transporters simultaneously, such as here in an open cast mine in Saxony. In this case, a drive station for a belt conveyor system has to be moved. Because this steel monster is nearly 50 meters long, the heavy load experts need to move it using 2 self-propelled transporters, wirelessly synchronized with one another. 1 4-axle line module and 1 8-axle line module are needed to transport this load, weighing a total of 130 tons, because the maximum permitted load per axle on public roads is 12 tons. The self-propelled transporter modules have either 4 or 6 axle lines. They share the same basic structure. A box section design with integrated tanks for air and hydraulic oil. This stiffens the chassis against twisting. It can withstand high loads thanks to strong crossmembers and reinforced outer sections. The principle: as little dead weight as possible and as high a load capacity as possible. Nevertheless, the frames for the 6-axle versions weigh a proud 11 tons naked. Installing the hydraulics in these 9-meter-long and 3-meter-wide steel beasts is very complicated. Multiple components need to be connected to different lines.
Now we come to the hydraulic tubing for level, steering, and transmission. The level tubing is for raising and lowering the chassis. Then we have the steering. This is the steering block, from where the steering is controlled. And the large tubes are for the drive system, the hydrostatic transmission. The blue thing here is a nitrogen reservoir to buffer the pressure peaks in transmission and steering systems. Here we also have the tube burst protection. We need that so that if a hose ruptures, the vehicle does not lower itself.
All tubes are bent in advance, following the plan exactly. Now the technicians need to cut them precisely to length. The hydraulic tubes for the drive system have a wall thickness of 5 millimeters because they have to withstand the most pressure, namely 420 bar. The cut edges now have to be deburred, both inside and outside. The technician widens the ends of the tube by inserting a conical sealing nipple. One end of the tube has now been stretched enough that the gaskets and the tightening nuts no longer slip over it. Once the 2 gaskets and nuts have been threaded on, the technician inserts a sealing nipple at the other end of the tube. Finally, a lubricant is applied to the gaskets. The technician can then install the hydraulic tube for the transmission system. He tightens the nuts to pull the flared pipe ends with their inner and outer gaskets onto the threads. Once the connections are tightened later, they will be 100% leak tight, even at very high pressures. In the meantime, the power pack has been painted, including the hydraulics, in order to protect them from corrosion. Before the motor and all supplementary components can be installed, the electricians get to work. They have to lay a large amount of cabling, with a total length of hundreds of meters, install control units and connectors, including for the power supply and electronic control of fuel supply, emission control, and cooling. Completion of the 530 horsepower power pack motor. The pumps for the drive system and the working hydraulics have already been installed, along with 3 of the enormous hydraulic hoses. Once the remaining hoses have been attached, the engine, which now weighs 1.6 tons, will be ready for installation. The braking system pneumatics and the electrics have already been installed on the painted frame of the chassis.
Hier können wir jetzt sehen, dass im ganzen Fahrwerk
Here we can see that all the electrical wiring has now been laid throughout the chassis. The electrical wires meet in our control boxes.
Die Schaltkästen sind für die Steuerung.
These control boxes are responsible for controlling the steering. Air pressure is fed into the chassis through these 3 pneumatic couplings. These then lead to hoses, which are connected to the valves, and these valves control the chassis braking.
For the next steps to prepare the chassis, fitter Jürgen Taufratshofer must turn the frame on its back. In order to protect the paint during this process, he attaches steel spacers with rubber mats to the self-propelled transporter chassis. The frame, which now weighs 12.4 tons, is rotated in 3 steps. In the first step, the lifting chains are attached in the center. After it has been hoisted up, the stand is removed. The frame is then set down with its less sensitive side on the floor. For step 2, the team attaches the lifting chains to one side of the chassis and secure them with enormous shackles. Now the trestles, with their steel-reinforced rubber supports, are placed under one side of the chassis. With the chassis hanging vertically, it's moved backwards and set down on the spacer studs. Fitter Jürgen Taufratshofer lays out steel-reinforced rubber pads on which the chassis temporarily rests. For step 3, the lifting chains are again attached to the center of the chassis. The final act of the rotation process, the chassis is replaced on the stands in an upside-down position. Now the fitter can install the next components of the chassis. This is the swivel head for one of the axles. It consists of an outer and inner ring and a worm drive, a key component of the self-propelled transporter's electronic multi-way steering. This allows a steering angle of 135 degrees in either direction. The worm drive turns the outer ring of the swivel head. The axle moves to the right or left, depending on which of the 2 hydraulic tubes is supplying pressure. Before installation, fitter Jürgen Taufratshofer scrapes clean the bottom of the swivel head so that it can be mounted precisely onto the chassis. He then checks that the hydraulic connections on the worm drive actuator are clean. Dirt in the hydraulic fluid can damage the entire system. Now, the fitter bolts the inner ring of the swivel head to the chassis frame. The swivel head must sit absolutely rock solid. The 24 bolts are therefore tightened to a torque of 220 Newton meters. Sven Stoffel is responsible for installing the hydraulic lines. He always connects the two axles of each axle line at once. He starts by attaching the two hydraulic hoses for the first axle to the control block. This has a magnetic switch. It governs the clockwise or counterclockwise rotation of the axle by applying oil pressure to one line or the other. He screws the other ends of the hoses to the hydraulic pump that drives the worm gear. Now Sven installs the hoses for the opposite axle. He also connects it to the hydraulic block that controls the two axles. In operation, the opposing axles turn in either exactly the same or exactly the opposite direction. The electronic multi-way steering makes the self-propelled transporter extremely maneuverable. Each axle line can be controlled individually. This means that even the tightest of curves are no problem, and it doesn't matter how big or heavy the load. The last step of the process. Sven Stoffel installs a so-called oil leak line on the hydraulic motor. This carries overflowing oil back to the tank to prevent the pressure in the motor rising too high and destroying it. The power pack is now ready for the installation of the large components. The technicians have already installed many smaller components.
Here we've installed lifting cylinders, locking cylinders for mounting on the chassis. Over here we have the air cylinder for the pneumatics underneath. We have already installed the control cabinet. If you look inside, we have two batteries, a distribution box, and here we have the pneumatic brake. Then we have the exhaust emission stack, which has two afterburner stages and complies with the Tier 4 final standard. One in the first injector, then if the exhaust gas composition is still out of the acceptable range, it's burned again in injector 2, and then it's measured again at the exhaust. If the exhaust gas composition doesn't lie within the limits, the engine will shut down.
Two other important components, the AdBlue tank and the two motor control units. A powerful machine also needs powerful cooling. The self-propelled transporter actually has two of these. First, mechanic Hugo Kischle hoists the double cooling unit for the hydraulic oil. It has a flow rate of 140 liters per minute. 100 liters for the propulsion system and 40 for the working hydraulics. So there's something to raise and lower the chassis. While the mechanic is securing the cooling unit, hydraulic engineer Max Beer is installing the connections. The lower one is the oil outlet, and the upper one the inlet. The fan is driven by a hydraulic motor. The pressure connection is on the right, and the oil return on the left. The second large assembly is a combination cooler for the motor and charge air. It has a flow rate of around 400 liters of water per minute. Now, hydraulic engineer Max Beer is adding the connections for the engine to the combination cooler. The heart of the power pack, the 530 horsepower 6-cylinder turbo diesel with 12 liters of displacement. In order to lift it with the crane, mechanic Hugo Kischle also needs a crossbeam, because the motor has to be attached to the chain at 3 well-separated points. This is the only way to ensure that the motor hangs exactly level as it is lowered into position. The first attempt failed. The motor doesn't hang level. Hugo has to make some adjustments and shorten one of the chains. The second attempt. Success. But before the mechanic can maneuver the engine to the power pack, he first has to unbolt it from the assembly stand. With all its additional components, the motor now weighs over 1.6 tons, plus the lifting chains and crossbeam. Great care is required when positioning the motor in the power pack. Any damage to the engine or other components would not just be very expensive, but would also completely derail the tightly scheduled manufacturing process. The final 1.5 meters before touchdown. Now, extra care needs to be taken to ensure that the large hydraulics and cooling water hoses are in the right position and won't damage any other parts. The last few centimeters call for precision operation of the crane control system. Hugo Kischle inserts the engine mounting bolts and moves the motor manually so that the bolts thread into the holes in the frame. The engine is in place, and the mechanic now has to get under the power pack to tighten the screws from a lying down position. Preparations before attaching the axles to the chassis. Electrician Mako Kühnel installs a potentiometer, a mechanically adjustable resistor on the axle swivel head's worm drive. When the worm gear turns, the resistance changes, indicating the steering angle of the axle. The second and the fourth axles on each side of the module are driven and braked by hydraulic pressure. Reversing the direction of the pressure causes the module to drive either forwards or backwards. This is one of the non-driven axles. That's why it needs an air-operated brake. The ride height of the axle, which weighs over 500 kilos, can be adjusted by means of a hydraulic cylinder. Now, the electronic control cables and the hydraulic hose have to be moved out of the way. Then, the fitter can position and carefully align the axle on the swivel head. To hold it in place, Jürgen inserts 30 bolts into the holes and tightens them. First with an impact driver, and then using a torque wrench. Due to their multifunctionality, the axles are subjected to extreme loads. They therefore have to be 100% secure.
The axle has a turning angle of 270 degrees total and hydraulic compensation of 30 centimeters up or down. The axle compensates when it drives over an obstacle. It works like this. As the axle drives onto the obstacle, it retracts. After passing the obstacle, it extends again and comes back into contact with the road surface. This keeps the loading surface level.
One more feature of the axle: it can tilt. This means that it can compensate for lateral irregularities on the track surface. When operating in difficult terrain, the combination of height control, axle compensation, turning angle, and tilting is particularly important, such as in this case here of transporting a belt conveyor drive station for an open cast mine. Passing under this belt conveyor with the load requires millimetric precision. It's only possible because the operator of the two self-propelled transporters has lowered the chassis all the way down by 30 centimeters. Otherwise, the heavy-duty transporter would have grazed against the belt conveyor, possibly damaging it. Another challenge in this transport operation is the curves that are so tight that the self-propelled transporter carrying the 50-meter load has to drive on the unpaved shoulder on the inside of the curve. The self-propelled transporter's hydraulic axle compensation keeps each axle in contact with the ground, while the cargo bed remains horizontal. The next curve is not just on a gradient, but also slopes from one side to the other. This would cause lesser all-terrain transporters to tip over. Not so for the self-propelled transporter. It raises the axles on the side of the cargo bed on the inside of the curve, while on the outside of the curve, the axles tilt to compensate for the uneven surface. It's only possible to complete this turning maneuver in such a confined space without shunting, thanks to the large turning angles of the individual axles. Before the wheels are attached to the chassis axles, Sven Stoffel needs to test the hydraulics. To do this, he first connects the leak hose, which carries the overflow oil away from the hydraulic motors. Then the pump line, that is, the oil inlet. And finally, the return hose to the hydraulic tank. In this test, all hoses are connected to the hydraulic pump unit. It's set to a pressure of 100 bar.
Also ich schalte alle Achsen zu.
So I connect all the axles, check the turning direction, and that the tubing doesn't leak.
Now Sven tests 4 axles at the same time to ensure they turn accurately and in unison. Perfect.
All axles turn in the same direction. That's great. The block is leak tight. And now we drive one axis to the end stop.
The end stop is strictly a safety device. In normal operation, the angle of the axle is measured by a potentiometer, which limits it to 135 degrees left or right. Sven checks that none of the hoses have been trapped. Then he uses a mirror to check whether the end stop on the right side has latched. Everything is okay. Then he turns the axle in the other direction.
Super.
Great. If the end stop does not latch, and if the potentiometer were to fail, the axle would then rotate in a continuous circle, and all the hoses would be ripped off.
Now pneumatics engineer Markus Treffler checks the air-operated brakes on the non-driven axles.
These are the 3 pneumatic air pressure ports. This is the supply. It fills the compressed air tank. Here's the coupling for the service brake. And this is a pass-through line. We need that when connecting several modules one after the other. The brakes are applied from the center outwards.
Markus pressurizes the pneumatic system to 8 bar. For testing purposes, he attaches a pressure gauge to the supply tank installed in the frame. First, he checks the parking brake, equivalent to a car's handbrake. Hitting the brake release button applies pressure to the parking brake spring mechanism. The spring contracts. The parking brakes should now be released. The pneumatic engineer now has to check each of the 8 axles one by one.
Good. Now they've all been released. Now if I pull the release button, all the parking brakes should be engaged.
Here, he also has to check each of the pneumatically braked axles individually.
Okay, now that I know that the parking brake works, I'm going to test the service brake. So I push the button all the way in so that the parking brake is off. For this, I need a new connector on blue for the service brake. And now I apply the brake with 6 bar. Now all the brake axles should be locked again. I'll go around and check that again. Doesn't move. Good. Now I've removed the pressure hose. And all the brake axles should now be free again.
So, both the parking brake and the service brake are working. Now Marcos applies pressure to the service brake again so that it engages. Then he removes the pressure hose and checks whether the system as a whole is leak tight.
Then we leave it for 10 minutes and check that we don't lose any pressure.
The result? The pneumatic brake system is completely free from leaks. For some transport operations, the self-propelled transporter also has to overcome steep gradients. The double braking system provides additional safety. The non-driven axles brake pneumatically, meaning they are activated by air pressure. The hydraulically driven axles brake hydraulically, by reducing the oil pressure. Sometimes, if the driven axles do not have enough grip, they even spin in reverse. At the power pack assembly area, it's time to install the tanks. To save weight, they're made of aluminum. The larger tank is for the hydraulic fluid. It holds around 1,130 liters. It has a filter at the top for the oil from the drive system and the working hydraulics. Mechanic Hugo Kichle inserts the fill level gauge, which the electricians will have to adjust later. Each of the 2 tank components has a pressure release valve similar to those on a car radiator. These open at 1.5 bar and let air out when the oil expands due to heating. The temperature of the oil is measured by the sensors that the mechanic attaches to the filters. Getting the bulky hydraulic oil tank into place is a tricky procedure, because there is already very little clearance in the power pack frame. Collisions with other components could cause damage. That in turn could mean that the mechanics have to take the power pack apart again. Done. Hydraulic engineer Max Beer attaches the hoses, and mechanic Hugo Kichle bolts the hydraulic oil tank into place from below. Then he has to attach sight glasses on the side of the tanks. These visual fill level indicators are provided in case the electronic ones fail. The next component? The air intake system, including air filter for the powerful 6-cylinder diesel engine with its 12 liters of displacement and 2,130 Newton meters of torque. Such a big motor also needs a correspondingly large quantity of motor oil. The tank can hold 60 liters of it. It uses blue connection hoses to ensure that there can be no confusion with the hydraulic oil connections. The last major component of the power pack will then be installed.
Here we have the diesel tank, which has a capacity of nearly 450 liters, while the 530 horsepower Deutz motor has a relatively high fuel consumption, from 10 to 70 liters, although there's no upper limit. Depending on the load, the consumption can be higher.
10 to 70 liters per hour of operation, of course. Fuel consumption shoots up, especially on long and winding uphill journeys. For example, in this operation to transport a 50-meter-long wind turbine rotor blade in the Black Forest. Here, the self-propelled transporter has to handle 400 meters of altitude with gradients of up to 20%. The transporter, weighing 85 tons, consumes 280 liters of diesel to cover 7 kilometers, including numerous maneuvers. Over 100 kilometers, that would be more than 4,000 liters. The 6-axis module of the self-propelled transporter has, as the name indicates, 6 lines of axles. Each line has 2 rotatable or steerable axles. Each of these 12 individual axles has 4 wheels. There are therefore 48 tires on this chassis. Each tire weighs a little over 50 kilograms. When the transporter is fully loaded, each of these tires bears 5.6 tons. The tire pressure has to be correspondingly high to prevent the tires from deforming too much under load. For safety reasons, the tires are placed in a steel cage, so they can be filled to 12.6 bar. This is important because if a defect causes the tire to blow out, bystanders could be injured or even killed. Each axle has 4 wheels. Fitter Jürgen Taufratshofer attaches a valve extension to the inside wheel. Then he uses a crane to lift it onto the axle and slides the holes over the stud bolts. The inside wheel is tightened together with the outer wheel. The fitter has to tighten the wheel nuts to a torque of 650 Newton meters. For this, he has a special high-torque driver with a reaction arm to counterbalance the torque. Once 2 wheels have been mounted on each axle, his colleague turns the axles so that the remaining 12 pairs of wheels can be installed. In the meantime, fitter Jürgen Taufratshofer bolts 2 brackets to the side of the chassis. These will be used in a moment to turn the chassis over. After all the wheels have been mounted, the chassis has to be moved from its inverted position and placed the right way up. To do this, the fitter removes the safety pins from the axles, so they lower hydraulically. The chassis is rotated in a stepwise process. The fitter attaches the lifting chains to one side using bolt shackles. He then places support blocks with steel-reinforced rubber pads in front of the steel brackets he just installed. The fitter uses the crane to tilt the chassis onto the brackets and support blocks until it's standing vertically. He then lifts it up and moves it to the edge of the production hall. Now he tilts the chassis again onto trestles at the front and rear ends. The next step? The lifting chains are moved from the sides into the middle of the chassis. Then it's a matter of hoisting again, removing the trestles and lowering the chassis to the ground. The 6-axle module is now ready. With a dead weight of 26 tons, it can carry up to 235 tons. By coupling together multiple modules, even larger loads can be carried. For example, in this shipyard in Altanova, 50 kilometers southeast of Istanbul. Each of these 2 newly built Norwegian cruise ships weighs an impressive 6,200 tons. The heavy logistics company Haraket now has to move these vessels one after the other from a dry dock into the floating dock. These steel monsters are 124 meters long, 22 meters wide, and 35 meters tall. Transporting them requires 200 heavy-duty axle lines with 1,600 wheels. They cannot be moved quickly. The transport operation, requiring numerous maneuvers, takes 4 full days to cover the 250-meter route. The two giants then stand just 1.5 meters from one another in the floating dock. The two components of the self-propelled transporter have now been completed. Next, Sven Stoffel has to check that they both perform at 100%.
The vehicle has already been filled with diesel and AdBlue. Now it still needs hydraulic fluid for the final commissioning.
The tank holds 1,130 liters.
We always use a filter when filling the power pack so that we can remove any particles or residues. This is because the pumps are very sensitive to fouling.
Nearly 40 liters per minute are now flowing into the power pack's hydraulic oil tank. Filling it takes around half an hour. Sven starts the 530 horsepower 6-cylinder diesel engine. He checks that the speed is set correctly and that the individual systems have enough oil pressure. The feed pressure is used to pressurize the hydraulic pumps of the motor itself. It must be between 28 and 38 bar. This value is good. Next check, the circulating oil pressure. This serves to cool the wheel motors that drive the axles. Just under 25 bar, also okay.
I'm going to set the pump pressure to 50 bar and the brake pressure. This brake pressure is not actually necessary for the new chassis, but if the customer has an older chassis which they'll use in combination or even on its own, they'll need it to activate the hydraulic brakes.
The pump pressure for driving the axles is also fine, as is the working pressure. This is used for steering, raising, and lowering the chassis. The working hydraulics also drive auxiliary equipment, such as a blade transporter for rotor blades. This rotor blade for a wind turbine in the Black Forest is 46 meters long and weighs around 15 tons. The crane operator has to feed the 72 bolts on the rotor blade into the holes on the blade rotator unit. But this doesn't have to be 100% exact, so transport manager Randolph Peters uses a trick.
Jiggling the adapter backwards and forwards makes it easier to insert the rotor blade's threaded rods into the adapter.
It's in. Now the crew bolt the rotor blade to the blade transporter with 72 nuts. The journey begins. Using the remote control, Randolph can not only steer and accelerate the module, but also turn the blade around its own axis or raise it up to 60 degrees. This is the only way this transporter can tackle the tight curves up the mountain without the rotor blade hitting anything. Even extremely narrow sections, such as this group of houses, can be navigated with the self-propelled unit. Randolph raises the rotor blade using the work hydraulics. Then he turns it, raises one side of the self-propelled transporter, and threads the rotor blade through the eye of this needle. Back at the Goldhofer production facility in Memmingen. The next step in commissioning the self-propelled transporter, testing the cooling unit. By short-circuiting an electronic sensor, Sven Stoffel simulates overheating of the cooling water. The cooling unit fan should then start up and reach at least 3,100 RPM. One of the fan blades has a reflector. Sven measures the speed of the cooling fan with a scanner. The result? The cooling unit works. Now Sven can attach the 8.6-ton power pack to the chassis. They call this the wetting. He and his colleague push the hydraulic hoses through the openings in the chassis so that they won't get jammed. They then make fine adjustments until the coupling eyelets are perfectly aligned and the locking pin passes through. Now it's time for the power pack's hydraulic cylinders.
Now we're going to attach the lift cylinders so that the power pack can tilt so it doesn't scrape along the ground on steep slopes.
Okay?
Ready?
Yes. And push.
Perfect.
Okay, that's it.
Sven bolts the lift cylinders to the chassis. Once the pressure hoses are attached, the wetting is complete and they can start testing the work hydraulics. First, Sven tests whether the power pack at the front can be raised and lowered. Then he checks the chassis by raising and lowering it in all directions. Everything is working perfectly. The working hydraulics are particularly important when the equipment is operating on uneven terrain, such as here in the Black Forest. When reversing, this self-propelled transporter and its load have to pass over a dip. The hydraulics ensure that the cargo bed remains horizontal. In the meantime, back at the Goldhofer production facility, Sven Stoffel has mounted a driver's seat on the chassis. He will need this for his measuring instruments during the first test drive. These will show whether the self-propelled transporter moves at the specified speed for a given pressure of the drive hydraulics. This is especially important when several modules are coupled together, or when several self-propelled transporters are transporting a large load together.
So, rückwärts, zweite Gang.
Reverse, second gear, full speed. 15.3 at 154 bar. Perfect.
Perfekt. Vorwärts, erste Gang.
Forward, first gear, full speed. 66 bar at 4.0.
4,0. Und rückwärts.
And backwards.
4,0.
4.0 at 67 bar. Excellent.
Einwandfrei. So, nach der
Everything looks fine for now. Speed's good, pressure's right, there are no leaks. It's fine in terms of speed too. Now we have to do an emergency stop test, a brake test. And then it's ready in terms of commissioning.
Sven carries out the emergency stop test with the remote control. He gives the self-propelled transporter a run-up, then presses the emergency stop button when it's at full speed. That means full braking power.
It's working perfectly.
Before the final tests, the self-propelled transporter still has to go through what is termed completion. Here, areas will be repainted where support wheels were previously attached, or where the paint has been damaged during assembly. Lashing eyes are attached to the side, which can be used, for example, to attach tension chains to secure the load. The power pack cover panels are made from powder-coated aluminum non-slip tread plate. 2 members of the completion team mount the bumper with integrated headlights and turn signals and then connect them to the power supply. To avoid confusion, the numerous connections for hydraulics, pneumatics, and electronics are labeled. The self-propelled transporter is now ready. The final test for the engine and chassis under partial load. Technician Daniel Bayer has had 30 tons of concrete loaded onto the transporter. The 6-axle vehicle can transport a maximum load of 235 tons. Daniel first tests the steering, driving through predefined programs. First, the circular test. This is possible thanks to the counter steering. The 3 forward axles steer in the opposite direction to the rear 3. Then the technician switches to 90-degree travel, also called crab steering. When rotating, the self-propelled transporter turns on the spot. This maneuver is called carousel steering. For the next steering mode, the frontmost axle is at 90 degrees. The subsequent axles are set to smaller and smaller steering angles, while the rearmost axle is stationary, the so-called windshield wiper mode. Once the steering tests have been passed, a forklift brings in an obstacle so that the hydraulic axle compensation can be tested. The individual axles rise when they drive over the obstacle and lower again when they have passed it. Finally, a check to ensure the axles tilt correctly. To do this, Daniel drives only 2 wheels of the axle over the obstacle. The tilting axle compensates for the unevenness as intended. Everything is working. The self-propelled transporter can now be handed over to the customer. Price for the 6-axle module, including the power pack, depends on the specific configuration, but is in the high 6-figure range.